Hydrogenation through addition is the addition of hydrogen to an alkene or an alkyne to produce an alkane. This reaction can only happen under very specific conditions, those being that the unsaturated compound must be dissolved in a nonpolar solvent and a platinum, nickel or palladium catalyst must be present. As an example, we have here prop-1-ene, which is an unsaturated compound because it contains a double bond that is reacted with hydrogen or a hydrogen molecule, again under these specific conditions. And under these conditions, the double bond between those two carbons would break, which would leave an additional bond able to be formed on each of those carbons, and those bonds then form with the individual hydrogens from that hydrogen molecule, which results in that prop-1-ene ending up as propane. This is an addition reaction because it is an unsaturated compound that is converted into a saturated compound, and we say it is hydrogenation through addition, and it is very specifically only possible under these two conditions. Halogenation through addition is the addition of a halogen to an alkene or an alkyne to produce a haloalkane, where the alkenes are the group 17 elements, those being fluorine, chlorine, bromine and iodine, all of them being diatomic. Important to note that halogenation through addition has no specific conditions, and as such we would say that it would occur almost spontaneously. As an example here we have but-2-ene, where we have a double bond on the second carbon that reacts with chlorine, and we know that this happens because the double bond, the second bond, is not as strong as the first, and as a result that bond would break and those bonds would then form with chlorine, and we would form 2,3-dichlorobutane, and that is halogenation through addition. One of the common applications of this type of reaction is known as the bromine water test, where bromine is a brownish color, and so when we add bromine water to a saturated compound being a compound that does not contain double bonds, there is no reaction, and because there is no reaction, the water would remain a brownish color. Whereas when we add bromine water to an unsaturated compound being one that contains a double or triple bond, there would be a halogenation reaction that takes place. As a result, the bromine would be removed from the water and the solution would turn clear. And so we can use the bromine water test to test for saturated or unsaturated hydrocarbons. Hydrohalogenation through addition is the addition of a hydrogen halide to an alkene or an alkyne to produce a haloalkane. This reaction can only happen on condition that there is no water present, and as an example here we have prop-1-ene that contains a double bond on the first carbon that reacts with hydrogen fluoride, and when there is no water present we know that the second bond would break because the second bond is weaker than the first, which leaves each of these carbons willing or looking to form a bond with either hydrogen or fluorine. Now what we can see is that there are two possible products, the one being 2-fluoropropane, where the fluorine has attached to the second carbon, the other being 1-fluoropropane. And so in addition reactions, for cases such as this, we use Markovnikov's rule, which says that the hydrogen will always attach to the carbon that has the most hydrogens. So in this case, we can see that the first carbon already has 2 hydrogens, and as a result, this first carbon would gain another hydrogen, and the fluorine would then be attached to the second carbon. So we say that 2-fluoropropane is the main product, and 1-fluoropropane is a byproduct. But when writing this reaction down, we typically only show it with the main product because that is what is given by Markovnikov's rule. Hydration through addition is the addition of water to an alkene or an alkyne to produce an alcohol. This can only happen on condition that there is water present in excess, as well as a strong acid, that being either sulfuric acid or phosphoric acid. As an example, we have here butene, which has a double bond on the first carbon, and when combined with water with these conditions, that being excess water and a strong acid presence, we break the double bond on that first carbon, which leaves each carbon looking to form new bonds. The water molecule then also breaks up into a hydroxyl group and a hydrogen ion, which can then attach themselves onto those carbons. And once again, we have two possible products. The first product here being butane 2-ol, where the hydrogen has attached to the first carbon and the hydroxyl group has attached to the second carbon. And the other product possible being butane 1-ol, where the hydroxyl is attached to the first carbon and the hydrogen attached to the second carbon. We can determine that the butane 2-ol is the main product by Markovnikov's rule, which tells us that the hydrogen will always attach to the carbon with the most hydrogens. So as we can see, this carbon number 1 already had 2 hydrogens to start with, where carbon number 2 only had 1 hydrogen. So as a result, we would say that butane 2-ol is the main product because the hydrogen has attached to the carbon with the most hydrogens by Markovnikov's rule, which leaves the hydroxyl to the second carbon. And we would draw this as butene plus water reacts to form butane 2-ol. We do not necessarily show butane 1-ol as a byproduct. Dehydrogenation through elimination is the elimination or removal of a hydrogen molecule from an alkane to produce an alkene. Theoretically, it is also possible to remove a hydrogen molecule from an alkene to produce an alkyne, but for the purposes of this syllabus, we only do alkanes to alkenes. The only condition required for this reaction to take place is that the reaction or the reactants must be heated, and we show that by drawing a triangle underneath the arrow. So as an example here, we have butane, and butane, when heated, would lose 2 hydrogens or undergo a dehydrogenation reaction. The question of which hydrogens to remove is answered by Zaitsev's rule, which tells us that we remove the hydrogen from the carbon that has the fewest hydrogens. So that is going to be, in this case, the second carbon. We remove our first hydrogen, and then we can see on the third carbon there's also only 2 hydrogens, whereas on the first carbon there are 3 hydrogens. And since we must choose 2 consecutive carbons, we would remove the hydrogen from the second and third carbon, which gives us as our main product butene, where now that these 2 carbons have lost their hydrogens, they now form a double bond or a second bond with each other, which turns this into an alkene. And then obviously we have our hydrogen molecule as a product as well. It is also possible, and very rarely or occasionally happens, that a byproduct is formed where Zaitsev's rule is not followed, but once again, we always draw, when we're drawing this reaction, we would only show the main product and hydrogen that are formed here. Dehydrohalogenation through elimination is the elimination or removal of a hydrogen halide from a haloalkane to produce an alkene. This reaction can only happen on condition that there is a strong base present in ethanol, that strong base being either potassium or sodium hydroxide, and that this solution is heated under reflux. Under reflux refers to it being in a closed container. So as an example here, we have 2-iodobutane, and when this is placed in a strong basic solution in ethanol and heated under reflux, we find that we are able to remove an iodine as well as a hydrogen atom, and we use Zaitsev's rule once again to determine which hydrogen atom is removed. And Zaitsev's rule tells us that we will always remove the hydrogen atom from the carbon that has the least or the fewest, which over here is this carbon, as this carbon only has 2 hydrogens. And as a result, our main product would then be butene, as well as obviously the hydrogen iodide that is formed. a byproduct, one that is formed not by Zaitsev's rule. But1-ene does exist, but happens very rarely, and so as a result, when we write this equation out, we would write that 2-iodobutane reacts to form but2-ene and hydrogen iodide. We do not need to specify what the byproduct is. Dehydration through elimination is the elimination or removal of water from an alcohol to produce an alkene. This reaction can only happen on condition that there is a strong acid present. That acid acts as a dehydrating agent. Usually we would use sulfuric or phosphoric acid, and that the reaction solution is heated, once again shown with the triangle underneath the arrow there. So as an example here, we can see that butane 2-ol can undergo this dehydration through elimination reaction, provided that these conditions are met, and we see that the hydroxyl group will be removed as well as a hydrogen atom. We can see that there are 2 possible hydrogen atoms that could be removed as they are adjacent to that hydroxyl group, and once again Zaitsev's rule tells us that we would remove the hydrogen from the carbon with the least or the fewest hydrogens, which means that our main product, the product that would be produced the majority of the time, would be but2-ene, where that hydroxyl and that hydrogen are removed, and those 2 carbons form a double bond to make sure that each of them has formed 4 bonds. And so we say that the main product is but2-ene. A possible byproduct would also be but1-ene, and once again we would normally only write this reaction by showing these reagents. It is not necessary to show the byproduct, and then obviously we have here produced water or eliminated water, which is why this is called a dehydrating reaction. Esterification can also be called a dehydration through elimination reaction because it also eliminates or gives off a water molecule. The esterification reaction, the general word equation, says that it is an alcohol plus a carboxylic acid that reacts to form an ester and water. The conditions are the same as a normal dehydration through elimination reaction, in that a strong acid, either sulfuric or phosphoric acid, is required as a dehydrating agent, and the solution is required to be heated. So in an esterification reaction, we have an alcohol. In this example, we have propan 1-ol that reacts with a carboxylic acid. Here we have ethanoic acid, and the alcohol is then seen to lose its hydrogen of the hydroxyl group, which combines with the hydroxyl group of the carboxylic acid that goes to form the water molecule that is removed, and then the remainder of these 2 molecules attach to each other in the form of an ester, which we call propyl ethanoate. The propyl, the part that is attached to the single bond oxygen, is always the part that comes from the alcohol, and the part that is attached to the single and the double bond oxygen is always a result of the carboxylic acid. And so as we can see in this reaction, because there's also a water molecule given off, we can also call this a dehydration reaction. Cracking is considered to be an elimination reaction because it sees us starting with a saturated compound and ending with 1 or more unsaturated compounds, which is roughly the definition for an elimination reaction. There are 2 types of cracking. The first type is where an alkane is broken into a shorter chain alkane and an alkene, or a number of alkenes. As an example here, we have pentane that under the right conditions is broken into a propane molecule, and then because there is now a shortage of hydrogens, the shorter chain, in this case the ethene, forms a double bond. So the first type of cracking is where a alkane is broken up into an alkane and then an alkene. The second type of cracking is where an alkane is broken into 1 or more alkenes and hydrogen is produced as a product. So as an example here, we have hexane, the alkane, that can be broken in two ways. The first way that we've shown here is where it breaks into two molecules, each of them forming a double bond, and then because there are now two double bonds, it means that there are excess hydrogens, and so we say that hydrogen is produced as a byproduct there. The second option would be for hexane to break instead of into two pieces, but to break into two carbon chains, three ethene molecules, which then, because of the excess hydrogen, then produces two hydrogen molecules. It is not possible, it is not required for you to be able to determine where the break would happen. Normally what would happen is a question would say something like hexane is broken into prop-1-ene, and then you are asked to identify what the other products are. So it is not necessary for you to be able to determine where it is broken or in what form the cracking takes place. That will always be made clear to you. All that you need to know is that there are two ways in which a molecule can be cracked. That is either into an alkane and an alkene, or into alkenes and hydrogen. The conditions depend on the type of cracking. The first type is known as thermal cracking, and that requires a high temperature and a high pressure. The second type is known as catalytic cracking, and that requires a catalyst. A substitution reaction is a reaction in which an atom or a group of atoms is replaced by another atom or group of atoms. Halogenation through substitution is the specific substitution reaction where an alkane is converted into a haloalkane, where we know that the halogens are the elements found in group 17 of the periodic table, those being fluorine, chlorine, bromine, and iodine. In order for this reaction to take place, the specific condition is that the reaction must either be heated or there must be UV light present. So we know that heating a reaction we show with a triangle underneath the arrow, or UV light is shown with the symbol HF. So as an example here, we have the halogenation of propane, where the propane is going to exchange one of its hydrogen atoms for one of the bromine atoms here. And that means that there are then two products possible, that being 2-bromopropane, where a hydrogen on the second carbon has been replaced by a bromine, and then one of the products there being hydrogen bromide. Or another possible product is 1-bromopropane, where a hydrogen on the first carbon has been replaced, and then obviously hydrogen bromide still as a product. And to determine which is the main product, we use Zaitsev's rule, which tells us that we will always remove a hydrogen from the carbon that has the least or the fewest hydrogens, which means that we are always going to remove, in this case, from the second carbon, which makes the main product 2-bromopropane, and the byproduct 1-bromopropane. And again, when we write this reaction down, we only need to include the main product and hydrogen bromide for the halogenation through substitution reaction. Hydrolysis through substitution is the conversion of a haloalkane into an alcohol, and there are two ways in which that can be done. The first is with sodium hydroxide or potassium hydroxide. The specific conditions required for this type of reaction are firstly that the haloalkane must be dissolved in ethanol. Second, there must be water present and sodium hydroxide or potassium hydroxide, and the reaction solution must be heated, again demonstrated with the triangle underneath the arrow. So in this example here, we have 1-fluoroethane that reacts with sodium hydroxide, and in the correct conditions, these three conditions here, what we would find is that the fluorine atom is substituted with the hydroxide, the hydroxyl group of atoms, to form ethane-1-ol, which is our alcohol, and then the remaining sodium fluoride. The second type of hydrolysis through substitution reaction is with only water, not with sodium hydroxide or potassium hydroxide. The specific conditions for this type of reaction are firstly that the haloalkane must be dissolved in ethanol, same as the previous reaction, and that there must be water present in excess. So in this example, we have 2-chloropropane that reacts with water, and when these conditions are met, we find that the chlorine atom is replaced or substituted by the hydroxyl group from the water molecule, which forms the alcohol propan 2-ol and then leaves us with HCl. Interconversion through substitution is the conversion of an alcohol into a haloalkane, most often using hydrogen bromide or hydrogen chloride, and this reaction can take place on condition that there is no water present. This reaction most commonly occurs with tertiary alcohols, that is an alcohol to which the hydroxyl group is attached to a carbon that is in turn attached to 3 other carbons. And what would happen in this interconversion reaction is the hydroxyl group that is forming that tertiary alcohol would be replaced or substituted with the halogen, in this case bromine, that is attached to the hydrogen, and that takes us from 2-methyl-butane 2-ol, the alcohol, to form 2-bromo-2-methyl-butane, as well as water. This interconversion reaction can often be seen as a reverse hydrolysis reaction, where hydrolysis converts from a haloalkane into an alcohol. Interconversion converts from an alcohol into a haloalkane.